In this video, I will go over some practice problems to help you prepare for your organic chemistry exam. Most of the practice problems will be centered on various addition reactions, organic synthesis, and mechanisms. So let's begin with this question. So here we're asked to predict the product of this reaction. Now, if bromine reacts with this alkane, what we have to do is to break the pi bond and attach each of the bromine atoms across the double bond of the alkane. And these bromine atoms must be added in an anti-addition fashion, such that the two bromine atoms have to be on opposite stereochemistry or opposite bonds. And this should be a product. Let's go to the next question. Here we're asked to predict the product of this reaction. Now there are two reactions, basically. The first one is where the alkane is reacting with bromine under light condition. So this first reaction will give us alkyl halide, in which the bromine atom will be attached to the more substituted carbon. And this will be the major product. Other monobromination products are possible, but this is going to be the major product. Now, in step 2, we are reacting this alkyl halide with sodium methoxide. To predict the product of this reaction, we need to ask ourselves the question, what type of alkyl halide do we have? So our alkyl halide is a tertiary alkyl halide. Now for the nucleophile, the sodium methoxide is a strong nucleophile because there is a negative charge on the oxygen, meaning that, which is an indication of an excess electron density around the oxygen. So that makes it a strong nucleophile. Now as a base, the compound is unstable. The methoxy group is unstable because the negative charge on the oxygen cannot be stabilized by resonance or by size. And so since this is an unstable base, it's quite reactive, and as such, we'll regard it as a strong base. So the sodium methoxide is a strong nucleophile that also behaves as a strong base. Now, this will result in a competition between SN2 and E2. So since our alkyl halide is tertiary alkyl halide, and our nucleophile could also, it's a strong nucleophile that could also double as a strong base, E2 is going to prevail. With that being said, we can go ahead and draw the E2 product. So since what we have here is a regular base, we will have the more substituted alkane as the major product. You could also have a minor product. The Hoffman product is going to be the minor product. So next question. This question asks us to provide the reagent that will be able to convert this tertiary alkyl halide to an ether. So you should apply retrosynthetic analysis to solving this problem. And retrosynthesis simply means working backwards. So since the product is ether, you want to ask yourself the question, how can we make an ether? Right. Also, another thing you have to look at is The only difference between our starting material and the product is that the chlorine atom in the starting material has now been replaced with a methoxy group. So the question then becomes, what reagent can we react with the tertiary alkyl halide to convert it to the ether? So that reagent must have OCH3 group. The question is, there are two types. We could make this a strong nucleophile, or we could make it a weak nucleophile. This is why it's quite important for us to ascertain the mechanism that this reaction will go through. Since our alkyl halide is a tertiary alkyl halide, this simply means that even though there is possibility of having SN2 and SN1, because this is definitely a substitution product, the mechanism can never be SN2 because we have a tertiary alkyl halide. So it has to be SN1 mechanism. If it's SN1 mechanism, definitely a nucleophile has to be a weak nucleophile. So the correct answer then has to be this alcohol. So this question asks us to provide the product of this reaction. So essentially, we need to ask ourselves the question, what type of group does these reagents add across the double bond of the alkane? It has to be hydrogen and hydroxy group. But this addition of these groups is usually done via Anti-Markovnikov fashion. So this simply means that I have to attach the hydrogen to the more substituted carbon, and the OH will go to the less substituted carbon. So to draw the product, I'll break the pi bond, and I will simply attach the OH group to the less substituted carbon, and that will be the product of this reaction. Next question. So here we're asked to predict the product of this reaction. To solve this problem, we have toxic chloride and pyridine. What does this reagent do? Toxic chloride and pyridine simply converts a bad leaving group. The OH here is a bad leaving group. So the toxic chloride and pyridine will convert that alcohol to a tosylate, which is a good leaving group. So essentially, we will treat this with the first reaction, which is toxic chloride and pyridine. The alcohol will get converted to tosylates. Next, we have to react this tosylate with potassium tetrodotoxide in the second step. So potassium tetrodotoxide is a bulky base, and the tosylate is a primary tosylate. You can treat the tosylate as the way you treat your alkyl halide. So when you react this primary tosylate with potassium tetrodotoxide, the prevailing mechanism is going to be E2. And as such, your product will be such that we have, if this is your alpha carbon and we have one beta carbon, all you have to do is to place a double bond between the alpha and beta carbon. So our product is going to be this alkane. This question asks us to predict the product of this reaction. Now, again, the first thing you want to do is to ask yourself the question, what type of group or groups does these reagents combination add across the double bond of the alkane? And how does it add the groups? So the groups that are being added by these reagents or the groups that are being generated by these reagents are hydrogen and hydroxy groups. And they will be added in a Markovnikov fashion. So this simply means that the hydroxy group will go to the more substituted carbon, and the hydrogen will go to the less substituted carbon. So to draw the product of this reaction, simply break the pi bond and attach the hydroxy group to the more substituted carbon. And that's all you have to do. The hydrogen will go here, but we don't have to show the hydrogen. Next question. This question asks us to predict the product of this reaction. So here, the two groups will be hydrogen and Br, and they will be added across the double bond of the alkane, and they will be added via Markovnikov addition. So what this simply means that the Br will go to the more substituted carbon, and the hydrogen will go to the less substituted carbon. So to draw the product of this reaction, simply break the pi bond and attach the Br to the more substituted carbon. Next, we're asked to predict the product of this reaction. To do this is ozonolysis oxidation. So all we have to do is to divide this molecule into two fragments by drawing a bond through the alkane. So this is going to give us two fragments, this and this. Next, we attach oxygen to both of the alkanes. So give this an oxygen and I give this an oxygen. And that's going to be the product. So these will be the product of this reaction. In this question, we're asked to provide the starting materials that will give this product. So we need to employ retrosynthetic approach to solve this problem. Now, since our product here is ether, and the Williamson ether synthesis require a strong nucleophile reacting with an alkyl halide via SN2 fashion. So this means I want to deconstruct this product into two fragments that make sense. So what I could do would be to cleave the bond here. If I did that, then I will have two fragments. Basically, I will have this, and I will have the methyl group. So how can I turn these fragments into meaningful reactants that can undergo SN2 reaction? So I need to make this into a strong nucleophile. I need to make the alkoxy group into a strong nucleophile by giving that oxygen a negative charge. So that makes that a strong nucleophile. Then all I have to do is to attach a good leaving group to the methyl, say bromine. In this question, we're asked to provide the product of this reaction. Now we need to recall that if we react an alkane with hydrogen bromide using organic radical, using an organic peroxide, which is also a radical initiator. And if this reaction is taking place under light condition, then the H and Br will be added across the double bond of the alkene via anti-Markovnikov addition. This simply means that the Br will go to the less substituted carbon and the hydrogen will go to the more substituted carbon. So to draw a product, we will simply have to attach bromine to the less substituted carbon. Here we're asked to provide the reagents that will convert this alkane to the alkane. So the reaction that involves conversion of alkane to alkane is hydrogenation. So just write hydrogen here, and then you could include any catalyst, which could be palladium catalyst, or you could use nickel catalyst, or you could use platinum catalyst. You only need to use one catalyst alongside hydrogen. Now, this question asks us to draw the mechanism for the reaction showing on the screen. Since we are reacting an alkane with bromine and the reaction is taking place under light conditions, then this has to go through radical mechanism. And in radical mechanism, there are 3 stages: initiation, propagation, and termination step. So what happens in the initiation step is that the bromine molecule will be split into radicals. So under light condition, the bond between the bromine atoms will break, and then one electron will go to one bromine atom, the other electron will go to the other bromine, and then you will have 2 bromine radicals. So in the initiation step, 2 radicals are generated. Now the radicals generated in the initiation step will then convert the alkane into an alkyl radical, which will in turn convert neutral bromine reactants to radicals also. So what happens essentially is that the bromine radical, one of the bromine radicals that is generated in the initiation step, will then react with the alkane. And the way this happens is that the bond between the hydrogen and carbon will break. One electron will go to the carbon. The other electron will be used by this hydrogen to form a bond with the bromine radical. So hydrogen bromide is formed, and we will also have an alkyl radical. The alkyl radical will then convert the bromine reactant, neutral bromine reactant, into a radical, and in the process, the product will be formed. So a neutral bromine reactant then combine with the alkyl radical. And the way this happens is that the bond between the bromine atoms will break. One electron will go to this bromine. The other electron will be used by this bromine to form a bond with this alkyl radical. So a bromine radical is formed, and alkyl halide is also formed in the process. And this is our product. So most of the products are formed in the propagation step. Now the bromine radical that is formed here will go on to convert more of the alkane into alkyl radical, and the alkyl radical will again react with neutral bromine reactant and convert it to bromine radical, and more of the product is formed. And this cycle will continue until all the starting materials, the alkane and the bromine, are all depleted or completely exhausted. And when the reactants, the neutral reactants, are completely exhausted, and now we're left with just radicals, bromine radical and alkyl radical, those radicals will then start combining in the termination step. So in the termination step, 2 bromine radicals can combine to terminate. So that forms a neutral bromine molecule, and the reaction gets terminated. Or we could have a bromine radical combining with alkyl radical to form alkyl halide. And this is a minor source of our products. Most of the products are actually formed in the propagation step. Another way we could have termination is the alkyl radicals can also combine with itself, which will form a byproduct. So this side product can also be formed in the process. This question asks us to draw the mechanism for this reaction. To draw the mechanism, we'll start by drawing out the alkane. Now, the geometry of the alkane is such that it is flat. As a result, the bromine molecule can approach the alkane from the top face or from the bottom face. So let's take it that the bromine approaches the alkane from the top face. What's going to happen is that the pi electrons in the pi bond can attack this bromine atom, and as such, a partial positive charge will be developed on the more substituted carbon of the alkane. The bromine can also donate electron simultaneously to this carbon of the alkane, in the process forming a bridgehead, and then this bromine will actually be kicked out. So we are going to form a bromonium ion, and this is going to be a bridge. And here is the bromide ion that is kicked out. Now, since the top face is already occupied by the bromonium ion, the nucleophile can only attack from the opposite side, or from the bottom face. This carbon would develop partial positive charge, as the bromonium ion will pull electrons from that carbon, from the more substituted carbon. Now, don't forget that this reaction also involved water. Actually, the bromine is diluted with water. So we have less concentration of the bromide, and we have more water molecules. So this simply means that since the bromine is in very low concentration, the bromide will also be in very low concentration, and the water has better chance of getting to this carbon first. So that water molecule will attack the carbon, and then this bond between carbon and the bromonium ion is going to break, and the excess electron will go to the bromonium ion, thereby neutralizing the positive charge on the bromonium ion. So a product will be such that water molecule, the oxygen will form a bond with the carbon, and now we have bromine on the opposite side as the hydroxonium or hydronium ion. Since oxygen have 3 bonds, it's going to get a positive charge. To get rid of the positive charge on the oxygen, we can then use the bromide ion for that deprotonation. So this is going to grab the proton. The bond between hydrogen and oxygen breaks. Excess electron goes to the oxygen, thereby neutralizing the positive charge on the oxygen. Eventually, we will have hydroxy group on this side, and we'll have bromine on this other side. And we'll also have a side product, HBr. Question here asks us to propose a reasonable synthesis to transform the alkane into an ether. So whenever you're solving synthesis problem, it's good to apply retrosynthetic analysis. And retrosynthetic analysis simply means working backwards. So try to work backward. At some point, try to work forward, and then eventually you connect the reactions. So in working backwards, what reactants are going to react in order to form this product? Retrosynthesis demands that you try to deconstruct the product into simpler fragments. So if I choose to break this bond here, then I will have this fragment. And I will also have this fragment. Since I know that making ether one of the good ways to make ether is to use a strong nucleophile and react that strong nucleophile with an alkyl halide via SN2 reaction, I can make this into a strong nucleophile and then just add a leaving group to the methyl group here. The next question would then be, how can I make this alkoxide ion? Of course, the alkoxide ion can be made simply by deprotonating an alcohol using a strong base. So the strong base here could be LDA, or I could use sodium hydride, or I could even use sodium. So either of these reagents will deprotonate, will pull off the oxygen from the oxygen, the hydrogen from the oxygen, and then it will confer a negative charge on the oxygen atom. At this point, we might choose to walk forward. In going forward, whenever you're starting a synthesis with an alkane, it's pretty easy to convert the alkane into a compound that can do many reactions. And one of such compounds is alkyl halide. So I'll try to convert this alkane to an alkyl halide. And the way to do that will be radical bromination. So if I react that alkane with bromine under light condition, then I will form this alkyl halide as the major product. The next question would then be, how can I connect the alkyl halide to the alcohol? I know that I can think of how I can add an OH group to an alkane to form the alcohol. So in other words, I will need to make my alkyl halide into an alkane and then treat that alkane with a reagent that can add hydrogen and OH group across the double bond of the alkane. Say I want to convert this alkyl halide to this type of alkane, and then I can now add OH and hydrogen across the double bond of the alkane to form my alcohol. So in order to make this alkane, I need to treat the alkyl halide with a strong base. So I have to perform an E2 mechanism. Since my alkyl halide is a tertiary alkyl halide, I can decide to treat it with sodium methoxide, a regular base. Of course, we will have competition between substitution reaction and elimination reaction, because this reagent is a strong nucleophile which could also function as a strong base. However, because our alkyl halide is tertiary, E2 mechanism will prevail. Eventually, I'll try to connect this alkane to the alcohol. Now I'm thinking, what kind of reagent can I use that will add hydroxy group to the less substituted carbon? So I'm going to use boron, which is stabilized by the solvent, THF, and I will use sodium hydroxide in the second step of the reaction with hydrogen peroxide. Now we've successfully proposed a reasonable synthesis to transform the alkane to the ether. Here we're also asked to show synthesis, a reasonable synthesis that could transform the alkane into an alcohol. Now, as usual, try working backwards whenever you have a synthesis problem like this. Try applying retrosynthetic analysis. And then the next thing will be to identify the functional group in the product. So this basically has an alcohol. Now I'm going to be thinking, what reagents can I use to make this alcohol? Right. So I can make an alcohol by treating an alkane with a reagent that can add hydrogen and hydroxy group across the double bond of the alkane. This time around, the OH has to go to the more substituted carbon. To make this happen, I will need water and catalytic acid, such as catalytic sulfuric acid. This will add OH group to the more substituted carbon, giving us the alcohol. At this point, I can also choose to work forward. Now, the starting material here is an alkane. The easier thing to do would be to convert the alkane to an alkyl halide. To make this happen, I'll react the alkane with bromine under light conditions. So the next thing would then be, how can I convert the alkane, the alkyl halide, to this alkane? Of course, we have to do elimination reaction. Now, mind you, in order to do E2 reaction, there are two types of bases we could use, a bulky base and a regular base. A bulky base is going to form double bond between this alpha carbon and this beta carbon, in which case your product will be this. But this is not what we're trying to form. We're trying to form the more substituted alkane. We're trying to form the Zaitsev product. So I'll have to use a regular base that will create a double bond between this alpha carbon and this other beta carbon. So we could use any regular base such as sodium ethoxide. Now we need to test the condition. So this is a strong base that can also function as a strong nucleophile. Strong nucleophile, which could also function as a strong base. So there is always a competition between E2 and an SN2. However, E2 will prevail since we have a tertiary alkyl halide. So these conditions are favorable for E2 mechanism. And this will be the synthesis for this problem. Here we're asked to predict the product of this reaction, as well as circle the correct operative mechanism. Now, the substrate, the tosylates, should be treated like an alkyl halide. So what type of tosylates do we have? It's primary. And tosylates are a very good leaving group. Now, the nucleophile we have is a strong nucleophile because there's a negative charge on the oxygen, suggesting excess electron density around the oxygen, making it a strong nucleophile. As a base, whenever you want to check if a base is strong or weak, look at how stable the base is. If it's stable, then it's a weak base. But if it's unstable, it's going to be reactive and as such will be considered a strong base. So in this base, there's a negative charge on the oxygen, and that negative charge cannot be stabilized by size or by resonance. Therefore, it's unstable base, making it a strong base. So since we have a primary tosylate and a nucleophile, a strong nucleophile that can also behave as a strong base, SN2 will prevail essentially. And in an SN2 mechanism, the nucleophile attacks the electrophilic carbon, thereby kicking out the leaving group. And so our product will be such that the ethoxy group is attached to the electrophilic carbon. In this problem, first of all, we need to predict the mechanism of this reaction and then decide what product is going to be formed. To make this decision, we need to try to find out what type of alkyl halide we have. So we have a secondary alkyl halide, and a nucleophile is a weak nucleophile since it doesn't have, there's no negative charge on the oxygen. And this is a weak base because this molecule is stable as a base. It's pretty stable. So we have a weak nucleophile that could also function as a weak base. These conditions are favorable for SN1 and E1. So this means we're going to have two products. We're going to have the SN1 product as well as the E1 product. For the SN1 product, all we have to do is to replace the bromine with the methoxy group. So here we're going to form an ether. For the E1 product, you will need to place a double bond between the alpha and the beta carbon. And these are the products of this reaction. In this problem, we are asked to predict the product of this reaction, as well as choose the right mechanism that this reaction will go through. I would like to draw the mechanism of this reaction. So alcohol is reacting with hydrogen bromide. The first step is going to be protonation. The OH attacks the proton and breaks the bond between the hydrogen and bromine, and the excess electrons go to the bromine atom. So you will form hydronium ion and a bromide. Now this is an excellent leaving group. And since oxygen has a positive charge, that oxygen is electron deficient, it's going to pull electrons from the nearby electron source, the single bond. So always draw your curved arrow from an electron source to an electron sink. So you draw it from the bond, from the center of the bond towards the oxygen. And now the water molecule is going to leave and you will form a carbocation intermediate. For the SN1 product, the bromide ion will then attack the carbocation. Again, when drawing curved arrow, draw it from electron source to electron sink. The bromide, the negatively charged bromine atom, or the bromide, is the electron source because it has lone pairs. And then the electron sink is going to be the carbon because it has a positive charge. That's how you can tell the electron sink. And when this happens, a bond is formed between the bromine and the carbon. So I'll choose SN1 as the operative mechanism in this reaction. Next question. We are reacting this alcohol with concentrated phosphoric acid. And we are also asked to choose the operative mechanism. Let's try to draw the mechanism of this reaction. If we treat the alcohol with phosphoric acid, the first step is going to be protonation. So draw your curved arrow from the electron source to electron sink. The electron source is the lone pair on this oxygen, and the electron sink is going to be the proton. The bond between hydrogen and oxygen is going to break, and the excess electron will go to the oxygen. So a hydronium ion is formed, and the conjugate base of the acid is also formed. How should we draw the next curved arrow? You need to identify your electron sink and electron source. The electron sink is this oxygen because it's electron deficient. The electron source is the bond between the oxygen and the carbon. So the oxygen is going to pull an electron It's going to pull electrons from this bond towards itself, thereby breaking the bond off. And you will then have the carbocation and water molecule. In the final step, we will bring the conjugate base up here. Now, this compound is not considered a nucleophile. It is a base. And this is because its tetrahedral structure makes it difficult to act as a nucleophile. So what this is going to do essentially is that it will pull off a beta proton. So if this is your alpha carbon, the carbon with a positive charge, then you could have, we have a beta proton here, we also have a beta proton here. To form, so there are two possible products that could be formed, but the major product will always be the Zaitsev product, the product that will give you the more substituted alkane. So since there's a proton there, the base will simply abstract that proton, and a double bond is formed between the alpha and beta carbon. And you would have this product. Of course, the acid is regenerated.